introduce you. There she goes. Okay. So we're very happy to have Caroline Morley with us today. So Caroline is an expert on exoplanet atmospheres. She's worked on everything from the highest mass free-floating objects, the brown dwarfs, and both hot and cold, and down to what the atmospheres of Earth-like planets would look like. And in particular, I know you'll be hearing a lot about her predictions for JWST, but her models are often gold standards for looking at planets with all kinds of observational techniques. So she got her PhD in astronomy and astrophysics from the University of California, Santa Cruz. There's a really outstanding group there that works on exoplanet atmospheres, including Jonathan Fortney and Mark Morley at nearby NASA Ames. And then she did a Sagan Fellowship at Harvard University. And in 2018, she moved as an assistant professor to the University of Texas at Austin, where she is now. And so we're very happy that she was able to join us, even though it's virtual and we can't totally treat you to the Carnegie experience. We're looking forward to your talk, Caroline.
Great. Thanks very much for the introduction. It's great to be here talking to you all today. And you'll have to come in 2024 to Austin when we're going to have our own total solar eclipse. We're just figuring out what conference we want attached to it, so you can expense your travel.
If you have an extra sofa, like, sign me up.
Yeah, sounds good.
All right, take it away.
Thanks. So I'm really excited to talk to you today. This is kind of a forward-looking talk about prospects for observing exoplanets in the upcoming years based on what we've learned so far about exoplanet atmospheres. So what I'm going to argue to you today is that the field of exoplanets is currently at a turning point. And so we're moving from one era, which was the era of HST and Spitzer, which is largely an era that is going to be coming to an end. And this was especially clear to me about a year ago when we had an event where I made Goodbye Spitzer cupcakes for the Spitzer Space Telescope. So we are now moving into a new era that I think is on many of our minds right now, as we've just passed through this cycle 1 deadline for the James Webb Space Telescope. And so this is a picture of the TESS Space Telescope and the James Webb Space Telescope. And as we're going to move into this era, this is really going to dramatically change our understanding of exoplanet atmospheres. So from this first era of exoplanet atmospheres, we've really been able to inventory our galaxy. So for the past 30 years, we've been inventorying our galactic yield of exoplanets and found a really broad range of exoplanets. So this is showing the period of exoplanets versus the mass, color-coded by how those planets were discovered. And so we have this big set, right? We have long period gas giant planets. We have the hot Jupiters, among the very first planets found. We're pushing now to seeing smaller planets, which I'll talk about a little bit later. And now we're really at a time when we want to observe these planets in more detail. And so there's lots of things we want to know. Some of the really basic things we want to know. So when a planet forms, how does that sculpt the composition of the planet? So from our tiny snapshot that we get in our own solar system, we can measure what, say, the enrichment of metals in an astronomy sense is in the atmosphere. So in this case, this is measuring the carbon abundance in methane in the atmosphere versus hydrogen versus the mass of the planets. And so if you look at the solar system planets, you can see that smaller planets are more enriched in methane. And larger planets like Jupiter are less enriched. And so we can, we're astronomers, we draw a power law through that. And this is interpreted as being more accretion of solids versus gas in the planet's atmosphere as you go to lower masses, to these ice giants in the solar system. And so one of the goals to figure out for exoplanets is, does this trend hold true for exoplanets? And then what else does this depend on? It's clearly not going to be this simple, a nice power law. For planets, planets are complicated. Planet formation is this kind of chaotic process. Another detail here, right, is what is the abundance of all of the different materials in the atmosphere. We think for planets, it's not going to be a kind of constant scaling of you get more carbon, you also get exactly the same amount more oxygen in your planet. We think that the elemental ratios, so things like the carbon to oxygen ratio, are probably set by your formation location in the disk. So as you get further away from the star, more materials condense into solids. And so you have different materials available in the gas phase versus the solid phase to accrete onto a gas giant exoplanet. So the water ice line, the CO2 ice line, and the CO ice line are all going to change how much carbon and oxygen are available in solids, solid grains, versus in gas. So if we can measure the atmospheres of these planets, we might be able to trace the formation location in the disk. And from our demographic survey of the exoplanets nearby, we found some mysteries that still vex us today. So we found, for example, this set of planets between Earth and Neptune in size, the super Earths and the sub-Neptunes. And we, of course, don't have an example like this in our own solar system, yet this seems to be one of the most abundant types of planets in the galaxy. One of the most common outcomes of planet formation is these super Earths and sub-Neptune sized planets. So we want to know more about these, right? Is it a tiny rocky core with this puffy hydrogen helium atmosphere on top? Is it something that accreted a lot of ices and then migrated? We really don't know exactly how these form and why we don't have any here in our own solar system. So this is something we want to know as well. So how do we go about actually looking at exoplanets and characterizing their atmospheres in detail? So here, for the most part during this talk, I'm going to be talking about transiting planets, because these are the planets that we've been able to characterize the best in terms of what their atmospheres are like for a really broad range of planets. So in this transit geometry, you take advantage of the fact that the planet crosses in front of the host star when it transits the planet and crosses behind the host star when it's eclipsed by the star. And so we can do transmission spectroscopy, where we see that starlight come through the planet's atmosphere before it reaches us, imprinting whatever molecules are absorbing in the planet's atmosphere. Those photons get removed from the light from the star. So we can see that effect. And I'll show you some examples of actual data that shows that in a few minutes. And then in thermal emission spectroscopy, we watch the eclipse. When the planet goes behind the star, we lose the light from the planet itself, so we can infer the thermal emission of the exoplanet. So some very beautiful looking data that shows this. So this is data from the Hubble Space Telescope from Kreidberg et al. 2014, showing eclipses on the left and transits on the right, broken up by wavelength. So you're looking from blue little bins of wavelength to red bins of wavelength in the infrared. And so this is a wavelength region from 1.1 to 1.7 microns on wide field camera 3. This has been kind of one of the workhorse instruments for doing exoplanet spectroscopy over the past decade or so. So we're looking at tiny changes in the eclipse depth and tiny changes in the transit depth that tell us what molecules are there in the atmosphere. So you can't see these changes by eye, but if we plot it up, you can see that indeed for the emission spectrum, looking at those tiny changes in eclipse depth, we get this, this feature here right around 1.4 microns that's due to water vapor absorption in the atmosphere. Likewise, in the transmission spectrum, we see the planet appears just a little bit larger at 1.4 microns, which is what you expect if you have water absorbing and increasing the apparent size of your planet via the transit depth, just slightly. So you can spend a whole PhD looking at this and taking these points in these two spectra and turning that into a water abundance in the atmosphere. So this is a retrieval that was done that tells us how much water is actually there in this exoplanet atmosphere. This is a generic hot Jupiter kind of planet, by the way. So this is all great. So we've been able to do this now for a number of planets. So what I'm arguing to you here is that the HST-Spitzer era of exoplanet characterization, we've been observing these exoplanets for 18 years now. In 2020, the first transmission spectrum was published in 2002. And so for each major result here for exoplanets, we started by looking at individual planets as kind of special snowflake planets. And we're now, 18 years later, beginning to live up to what has always been the promise of exoplanet science, which is that instead of just having this snapshot of 4 planets like we have in our solar system, we have a whole ensemble of planets around all kinds of different stars at all kinds of different distances from their host stars. So we can look at trends and understand the physics and chemistry of these atmospheres by looking at trends in the properties of these planets. So when we look at now a large number of these transmission spectra of exoplanets, this is publishing a whole set of hot Jupiter transmission spectra from HST at the short wavelengths and then Spitzer at these 2 mid-infrared points. You can see that there's a diversity of behavior, and what we're looking at here is that we can see a whole range of different atoms and molecules. So water is now regularly detected. The alkali metals are routinely detected to high significance in these hot Jupiter kinds of planets. So we can then take this kind of result where we see how much water vapor is in each of these spectra and put that on our very simplified mass metallicity plot that I showed you earlier that had our solar system planets, Jupiter, Saturn, Uranus, Neptune, the metal enhancement in terms of their carbon versus the mass of the planet. And now we can start to add on some exoplanets, albeit with somewhat bigger error bars, and now based on their oxygen abundance in the form of water, because we can't measure carbon yet with just this 1.1 to 1.7 micron data. So what you can see here is that we're starting to put these planets on, so that's good. I would say that we're seeing tentatively a diversity in what we're seeing, but to first order, it's kind of you don't really see a trend right now. We don't quite have enough of this data to high significance to really understand what's going on here and see, the error bars are just a little bit too big to be able to see trends in this the way we can for our solar system planets. But this is certainly what we're trying to do here. Okay. The second thing that we see to really high significance now, and something that I've studied a lot in my work, is that clouds and or hazes, we can't really tell the difference between clouds and hazes. I'll talk about a little bit what the differences are here. We see that these things are important in exoplanet atmospheres. So now I'm showing you the same plot here and now pointing out that these are stacked from where we see the largest features, so large alkali features, large water vapor features. So these are interpreted as being the most clear atmospheres, the fewest clouds and hazes, stacked down here towards the ones where we see no features at all. So we either see that these spectra look like they're just a flat line all the way across the optical to the infrared, or they're slightly sloped. And so what's happening here is that the clouds are obscuring what we can see. The clouds are above where that gas absorption would have been that creates these features. And so instead we see these muted flat spectra. Okay, so we can now measure essentially how flat versus featured is the spectrum versus any property of the planet that we're interested in to try to understand something that's physically going on in these planets. So we can start to leverage trends to understand which clouds or hazes are forming, because just from a flat line, I can't tell you what material is actually absorbing in the atmosphere. Okay, so let's start with hazes. So hazes, here I'm using haze to mean anything that's formed via photochemistry. So the idea here is that you take an atmosphere that's rich in, say, methane, bombard that atmosphere with UV light from its host star. This starts a whole chain of chemistry by breaking up that methane, and then chemical reactions occur that start to give you longer chain hydrocarbons, Our photochemical models can take us as far as these soot precursors that I've listed here. And we think that the conditions are right, that these should start to form into kind of long chain hydrocarbons, organics, polymers, soots, things like that, that actually condense in a warm planetary atmosphere. So what kind of trend do we expect to see when we have these hazes forming? So we expect that you get the most of these soot precursors in atmospheres that start out really methane rich. So if you look at the temperature of the planet, which is listed above here, these are all for models, you end up with the most of these soot precursors in a photochemical model in kind of 600 to 800 Kelvin atmospheres. And then you end up with this really steep drop off when you have an atmosphere that, because it's hotter, the chemistry at hotter temperatures gives you CO. Most of your carbon is locked into carbon monoxide instead of in methane. Carbon monoxide has a stronger bond. It's harder to break up. You don't start this whole chain of chemistry that gives you these soot precursors. So we would expect to see that at hot planets, so anything kind of 1,000 Kelvin and hotter, you would see clearer atmospheres. And then as you go to cooler and cooler planets, you would expect to see more of these photochemical kind of hydrocarbon or organic hazes in the atmospheres. When we include these hazes for some of the observed planets that we've seen, so this is for a planet GJ1214b, which is our canonical cool sub-Neptune sized planet, 2.7 Earth radii, orbits a cool star, has a beautifully measured totally flat spectrum. We can match that totally flat spectrum with our models that include these photochemically derived hazes. So we can do this for this planet. We can, spend a bunch of HST time and do this for a bunch of other sub-Neptune and Neptune-sized planets. And this is what we find. So this is taking that exquisite flat spectrum for GJ1214b and making it all into just this single point here with teeny tiny error bars, because this is a really high precision spectrum that tells us that the amplitude of that feature is really small. It's really flat. So that's this point. Then we've done that for each of these other points as well that actually have water detected in them for these clearer objects. So what we see is that as the atmospheres of more Neptune and sub-Neptune sized planets are observed, the data actually match this prediction, that the cooler planets down here all seem to have those hazier, flatter spectra than the clear, warmer atmospheres here. So this is at least tentatively holding together that it appears that the cool atmospheres have these hazes in them. Okay, so that was hazes, photochemistry making these organic hazes. What about clouds? So models predict that the temperature will control which clouds form in our atmosphere. So it's a cloudy day in Chile, right? We've crossed this water condensation curve in Chile, where it's in the atmosphere, the water is condensing into either liquid or solid water vapor. So these are model pressure temperature profiles and condensation curves here shown as these gray dashed lines. So the idea here is that, say for water, to the right of this, it's hot enough that water is in the vapor phase, it's absorbing as a water vapor gas. To the left, it's cold enough that water condenses into solid ice for the most part in these atmospheres. And so you form a cloud where the pressure temperature profile meets that condensation curve. So for Earth and the solar system planets, we're way over here on this cold side of the plot. But for the exoplanets that we're observing, we form all kinds of different cloud materials, should be able to condense in the atmosphere. And so the most important of these end up being these silicate clouds over here that condense between kind of 1500 and 2000 Kelvin. You condense things that are rocks on Earth, things like enstatite, forsterite, iron, corundum on Earth, and these condense into these kind of dusty clouds in these planet atmospheres. And so what we would expect to see is that as you go from really hot objects, you'd have very little cloud forming material that you don't see them anymore. And so we can do this for hot Jupiters.
Sorry, Caroline. I
Yeah,
hate to interrupt. You just paused for a few seconds there.
Okay, yes, I see something that says your internet connection is unstable. Am I back now?
Yep, you're fine now. It
Okay.
just cut out for a few seconds. You might want to go rewind about 5 or 10 seconds.
Okay, yeah.
Mhm.
So the idea here is that if we look at planets that are a range of different temperatures, we would expect to see really hot planets would have very little of this silicate material forming clouds because it's too hot. As they cool down, we would expect to see more of these silicates form into clouds. We would see more muted spectra. And then as we get even cooler, they would sink below where we can see them, and we might start seeing features again if it's these silicate clouds that are muting our spectra. And this is indeed what we appear to see in these exoplanets. So this is plotting the temperature of the exoplanet, the equilibrium temperature on the x-axis versus the water band amplitude, so how big that water vapor feature is on the y-axis. You can see for a clear model, you'd expect to see the feature get stronger and stronger as you go to cooler temperatures. For a cloudy model, you expect to see this feature here due to silicates forming. And then in fact, over here at these cool temperatures, colder than 1000 Kelvin, we again see these photochemical hazes, these organic hazes start to form. And so to first order these models that include silicate clouds at hot temperatures and organic hazes at cool temperatures appear to fit this these data points, which are all these transmission spectra of hot Jupiters. So this is what this appears to be in these atmospheres. Okay, so the last kind of highlight from the HST-Spitzer era of exoplanet characterization is about the chemistry of these planetary atmospheres. And it turns out that the chemistry is pretty complex, but that these emission spectra, so looking at eclipses now instead of transits of these planets, end up being a really powerful tool for probing this chemistry. So one of the most perplexing results that's actually been seen from pretty early on in the HST-Spitzer era from the Spitzer Space Telescope is for the warm Neptunes. So this is a spectrum, this is 2 points, so kind of spectrum, of GJ436b. So you can see that it has this large eclipse here at 3.6 microns in the Spitzer bandpass, and then this small eclipse here. It's almost invisible at 4.5 microns. And so it's actually really hard to make a model that fits this for reasons that I will discuss. And it turns out that we've been thinking about this particular planet, GJ436b, for a while, but the same thing actually turns out to be true for other warm Neptunes as well. So this is another phone number, GJ3470b. It's a slightly cooler, warm Neptune-sized planet. And so this is surprising because what we would expect for these objects, these are something like 700 to 900 Kelvin objects, we would expect them to have a lot of methane in their atmospheres. And they don't. We don't see this methane absorption feature. We instead see that these objects are all bright at 3.6 microns and faint at 4.5 microns, where we have this CO and CO2 feature. So you need both CO and CO2 to be absorbing to end up with so little flux coming out at 4.5 microns. And so I'm going to very rapidly go through the series of hoops you have to jump through for a planet this temperature to actually get into a regime where we have the chemistry that we need. So the first step you have to do is increase the metallicity. So here we're always trying to push these blue lines, the methane, to as low numbers as possible. Somewhere in the part per million range is what we need to match the spectrum. And we want as much CO and CO2, so the red and black lines, as possible. Okay, so chemistry. We can increase the metallicity. We can increase the internal temperature. This sounds like a sort of arbitrary thing to do, but it turns out that these objects are all slightly eccentric orbits. And so we think they're actually being tidally heated in their interiors, just like the moons in the Saturn system are being tidally heated in their interiors. So we think that's happening for these exoplanets as well. Okay, so we do that, good. And then we can mix that chemistry up. So we assume that the mixing is happening really vigorously in these atmospheres. We mix that chemistry all the way up to the top. Okay, so we took my 4 data points, there's actually 6 data points for this planet, threw in a bunch of physics, right? A bunch of physics and chemistry that I stepped through too quickly. But it turns out that even with all of that physics and chemistry added, like as many knobs as we could think of to add, we still can't perfectly match the spectrum of this planet. To actually match it, you need to kind of just vary your abundances arbitrarily using a retrieval where you can just change anything. We can't actually figure out what physics and chemistry get us to the point where we can match this data. So this is kind of still a mystery, that some of these planets appear to have no methane and lots of CO and CO2, but not all of them. So if you plot up other hot Jupiter and hot Neptune sized planets, some of them in this temperature regime actually do have methane absorption in their atmospheres. So the punchline here is that we haven't figured this out yet. So there's stuff that's going on in the chemistry that we don't yet understand from our spectral photometry that we've been doing with Spitzer. Okay, fabulous. So these are our 3 punchlines from the HST-Spitzer era. So exoplanets have this really diverse range of molecules that we're regularly detecting in their atmospheres. We think that silicate clouds and organic hazes are really important in shaping the overall shape of those transmission spectra that we've observed. And we figured out that the chemistry of planetary atmospheres has aspects that we basically don't understand. So the emission spectra are really powerful tools for diagnosing this, but we still have a lot of work to do here. And we've moved from this regime where we've looked at individual planets, our kind of favorite individual planets, to looking at a whole ensemble of planets and being able to leverage the trends that we see to understand physics instead of having to understand everything from looking at a single object. And so now we're at this really special time where the TESS mission is flying and discovering new planets, and James Webb is launching next year and will really revolutionize our ability to probe these atmospheres. So I want to talk first a little bit about TESS, because when I think about this hard enough, it's really profound to me that we're going to reach this era where we have totally mapped out our neighborhood and found essentially all of the transiting planets in our solar neighborhood. So this is going to be a movie where we scale out from looking close to our solar system to scaling out to look at the galaxy. And you see each of the planets that were detected either by not Kepler or by Kepler. So these are all transiting planets. So we map out which planets we've found, and you can see that. Yeah, I'll just play it. So you can see all of these planets. You start to see the closest one in a second. This is from a few years ago. You start to see some of our favorite planets, some of which I've shown you spectra of. And as we zoom out, you see the direction that the Kepler Space Telescope looked, where we've been able to see all of these planets out to very large distances. You know, this is over 4,000 light years from us. So there exists that many planets all over, right? But we've only been able to look in this one direction. But with TESS, we're surveying all of the nearby bright stars for transiting planets. And so when you look at the predictions for what TESS will find, these were predicted before TESS was flying, but we should be able to update this figure soon once TESS has kind of finished its mission. You see that TESS will actually be able to find all of these planets that are quite nearby to us and dramatically change our picture of the solar neighborhood. And so we expect to find thousands of planets with TESS. And it's not going to be a question anymore of, are we going to find a better target to look at in a given class of planets? Like, we're going to find all of them around the nearby stars to us. So I think this is really going to be a switch for exoplanet scientists, where you know, there aren't more planets that are going to be there in our local neighborhood. We're going to have found them all, which has never been true in my lifetime, right? We've always been able to look at nearby stars and find more planets around them, but we'll have found all of the transiting planets. So TESS is going to find, as I said, thousands of planets. It's going to find the best, especially sub-Neptunes, for atmosphere characterization. Why are they the best? They're the best because they're around stars that are brighter than other stars that, say, the Kepler Space Telescope has revealed that all of these planets are abundant, but a lot of those are around more distant stars that are faint. We'll be able to see for TESS, these are largely around stars that are going to be much brighter. This also allows us to learn more about those systems. We can do things like following them up with radial velocity surveys and things like that. Okay, so for most of the rest of this talk, I'm going to talk about what we want to do with James Webb and kind of what the major breakthroughs are going to be here. So the first era of James Webb science will allow us to actually go back to our era where we look at our favorite kind of cherry-picked, interesting planets with interesting mysteries about them to solve some of these mysteries. And so one of the ones I'm most excited about is what's missing in our understanding of these Neptunes, right? This planet I showed you before, where even if we throw all of this physics into it, we can't actually match these data points here. The pink line that actually kind of fits this data is from a retrieved spectrum where we just change all of the abundances willy-nilly. The green line is our best fit from actual physics and chemistry. So this is going to be amazing. We're going to go from, say, these 2 points here, these 2 beautiful Spitzer points, to with a single eclipse from the NIRSpec instrument on James Webb, we'll be able to get a spectrum that looks like this and actually be able to see, okay, this really is bright at these wavelengths but has methane here. We'll be able to see these CO2 and CO features and retrieve those abundances and really start to figure out if there's something else going on in these objects that we didn't predict. We'll also be able to look at longer wavelengths as well. So this is predicting what we'd be able to do with three eclipses with MIRI from 5 to 10 microns. And you can see there's lots of features here as well that we'd be able to see. And I think we're just figuring out what we can do with this whole set of data. Thermal emission will also potentially allow us to see molecules in planets that have these really flat transmission spectra. So what we've shown is that for these planets that have hazy or cloudy atmospheres that have these flat spectra, especially for the hazy objects, we can actually start to see the molecules that are forming in these atmospheres for these planets that have otherwise been kind of impenetrable. And we'll also, with the broader wavelength coverage, clouds and hazes have flattened a lot of the near-infrared spectra, but clouds and hazes have more opacity in the near-infrared than they do in the mid-infrared. Because these are pretty small grains, they end up being much more clear at longer wavelengths. They don't absorb as much of the light. And so what we expect to see is that even for planets that are completely flat at these short wavelengths that we've been able to look at so far, we expect to start to see features again at longer wavelengths. And so this is simulated data of what James Webb can do for a cloudy versus hazy atmosphere for this planet that has this flat near-infrared spectrum. And we do think that we'll be able to see features out in the mid-infrared, which will be really exciting. Okay, and then I argued to you that from looking at these trends in the water vapor abundance versus equilibrium temperature, that I can tell you that there's silicate clouds forming in these objects. But with James Webb, we're actually going to be able to look at this 10 micron region where silicate itself has a strong absorption feature. So this has actually been seen in a brown dwarf. This silicate feature has been seen in this brown dwarf here. You see this kind of broad feature in here. This is interpreted as being silicate clouds in a brown dwarf. So we'll be able to do the same thing for exoplanets that we couldn't do with Spitzer IRS for exoplanets. So I have a student, Jessica Luna, who's been working on this. And this actually turned out to be really cool. So refractory clouds, so depending on exactly how your silicate is forming and what exactly, whether you form a crystal, whether you form kind of a glassy sphere, whether you form into enstatite or forsterite, how much iron is in there versus magnesium, all of these details turn out to matter in terms of what the optical properties of the material is, which is great because that means that we can actually use the location of the peak of this absorption to tell some of the chemistry, some of the kind of crystalline structure and things like that of these species. So we'll be able to tell the difference between a number of these different species and the particle sizes and things like that as well. So I think this is going to be really exciting for you know, really nailing down our understanding of these clouds. And then, so James Webb will also allow us to observe all kinds of new objects that we really haven't been able to observe in detail before. So I'm going to talk about two classes of objects that I think are going to be some of the most exciting science coming out of the first couple cycles of James Webb. So the first is objects that are colder than we've ever been able to observe in detail before. And the second is objects that are smaller than any planets we've been able to observe before. So we'll start with cold things. So from the ground a few years ago, we measured the first spectra of a 250 Kelvin free-floating planet outside of our solar system. This is one of my favorite objects. I really have a soft spot for WISE 0855. So this is a 250 Kelvin object. It's planetary mass. We can't tell the mass because it's just free floating by itself, but it's somewhere between 1 and 10 Jupiter masses, depending how old it is. And we have an L-band spectrum that I published that shows methane absorption. And we have a M-band spectrum here that shows water vapor features in the atmosphere. One of the really interesting things we see is that this object actually looks quite distinct from Jupiter, even though these objects are similar in terms of what their compositions are, largely, you know, hydrogen-rich, methane-rich, water-rich. But we see that Jupiter has a big phosphine absorption feature here. We don't see that in WISE 0855, and a few other interesting differences as well. And so James Webb is going to blow this all away. Like you run the simulations for what James Webb will do for this, you know, faint object that's bright in the infrared. This is what James Webb was designed to do, largely for extragalactic people, I think, but it's going to be amazing for this brown dwarf science. So the thing that I'm most excited about is that we'll actually be able to measure, we think, deuterated methane in this object's atmosphere. So to give you a little background of why that's interesting, the deuterium to hydrogen ratio is something that traces how objects form. We expect that the more ice you accrete into a giant planet atmosphere versus gas, the more enriched in deuterium you end up. This is, of course, also used to measure things like atmosphere loss for terrestrial planets. So this is kind of a pathfinder for that kind of science as well in the more distant future. And deuterated methane has this strong feature, is actually observed first in Jupiter's atmosphere in the 1970s from ground-based spectra. So this is an example of the kind of size of error bars we'll get for this object WISE 0855. You can see it will give us these really exquisite spectra, and we'll be able to actually see to really high significance this CH3D feature. The strongest feature is right at 4.55 microns. So that'll be really exciting. It'll let us trace things like the masses of these really cold brown dwarf atmospheres, test our understanding of where deuterium fusion turns on for these objects. So it's going to be really cool. Okay, so that's objects that are colder than ever before. And now I want to spend the last couple minutes talking about rocky planets, because I think everybody in the field of exoplanets is excited about the idea of being able to characterize rocky planets in more detail using James Webb. And so what I think is definitely true is that James Webb is best matched for hotter rocky planets, not truly habitable planets. And so I think James Webb will be really useful for kind of 3 categories of terrestrial planets based on how hot they are. So There's objects that are so hot that they're actually falling apart. They're being like vaporized apart and torn apart, and we can see that happening with Kepler. There's objects that are so hot that they're stable, but their surfaces are actually melting, and so they have these lava oceans on one side. And then there are slightly cooler objects that are in the kind of regime of something like an extrasolar Venus, or a little bit warmer than that, that are so hot that they've never had an ocean, like a liquid water ocean, on their surface, but nonetheless might retain some of their volatiles. So today I'm only going to talk about this set of objects, because I think that's really interesting for the question of what volatiles end up retained for billions of years around rocky planets. So I'm going to talk about these ones that are not in the like melting surface kind of hot regime, but that are kind of extrasolar Venuses. So the idea here is that we can assume the planets are probably all born with some kind of volatiles inside them. So you probably have a combination of mixing of ice-rich material from beyond the snow line during your planet formation process. You probably have volatile-rich planetesimals, things like hydrated minerals, carbonaceous chondrites. So we're forming planets that likely have volatiles locked up in their interiors. All planets that start with kind of that setup should outgas at least some amount of carbon dioxide. So in fact, Venus and Earth both have, to first order, the same amount of the CO2 reservoir, also the nitrogen reservoir. And then not having an ocean keeps your carbon dioxide in your atmosphere. So on Earth, that doesn't happen because we dissolve the carbon dioxide and then it ends up in carbonate rocks in the interior of our planet. But not having an ocean keeps your CO2 in the atmosphere. Every planet, likewise, should also outgas water vapor into the atmosphere, especially if you don't have an ocean that's keeping it on your surface. Okay, so that's our like really super simplified picture of planet formation. And so that gives us a planet that starts with CO2 and water vapor in the atmosphere. And then from here, we don't actually know what's going to happen in many of these planetary systems. Most of the planets that are in this regime that we're going to be able to observe with James Webb orbit really small stars. And that's because the planet size is larger relative to the size of the star. So we're really looking at these very non-solar type stars and the planetary systems around them. So we don't know how the atmospheric escape process is going to work from those. There's actually a lot of consternation in the community that many of these planets are going to lose their atmospheres. Okay, so we have these kind of testable scenarios. The first is that maybe many of these planets are super Earths. They're larger than the Earth. They're high gravity. Maybe planets around quiet stars will actually totally retain their outgassed atmospheres. And for these extrasolar Venuses, we'll see both CO2 and water vapor features in the atmosphere. That would be really exciting. Maybe these planets end up kind of like a true extrasolar Venus, that planets that have no oceans always manage to lose their water vapor to space, that you have interactions in the upper atmosphere that break up your water vapor, send your hydrogens away, and you end up with planets that just have largely CO2 atmospheres. Or maybe these planets around these smaller stars are under such conditions where they end up completely being stripped of their atmospheres, and we just have a bunch of little rocks floating in space instead of having atmospheres around them. And so this set of scenarios is testable with James Webb in the first couple of cycles. And so the way that people have proposed to do this is by looking at the how much recirculation you actually get from, say, a thick CO2 atmosphere. How much heat are you actually bringing from the day side of the planet around to the night side? So the idea here is that if you have a thick atmosphere, you circulate that heat from your star around your planet, and you end up with a planet that has a very similar temperature on the day side and the night side. So this is true for Venus, it's true for the Earth. You have pretty much the same temperature on day and night. So what happens is you can observe the phase curve. In this case, this is real data from the Spitzer Space Telescope for a rocky terrestrial planet. And you can observe the phase curve. And in this case, you see that it goes from being really cold on the night side of the planet here, just after the planet's transit, which is right here around orbital phase, right at orbital phase 0 is the planet's transit. You see the day side come into view here, and the planet gets hot on the day side. It's super bright on the day side. The secondary eclipse is here. We lose all of the light from the planet, and then the day side rotates out of view again. So what we see here from the Spitzer data is a huge day-night temperature contrast seen in this phase curve. This tells us that this planet does not have an atmosphere that's circulating the heat from the day side to the night side. And so what we think we can do is, by measuring just this secondary eclipse depth, which tells us essentially what the day side temperature of the planet is, we'll be able to map out for these hot terrestrial planets which of them have thick atmospheres and which of them don't. And so this is showing the temperature versus essentially how easy this is going to be to do. Is this ESM number here easier on the top of the plot than the bottom? And so you can see that we'll be able to map this out for many of these objects that are hotter than about 400 Kelvin to really test this question: is there an atmosphere? If there is an atmosphere, then we can start to dedicate kind of more time for studying those planets that have atmospheres. And this is the kind of spectra that we will be able to measure. So this is making simulations for TRAPPIST-1b. This is an object that's about 400 Kelvin. It's kind of on the coolest of these hot planets that I've been talking about. And we'll get a spectrum. If it looks something like Venus, we could get a transmission spectrum that looks like this in the near infrared, and an emission spectrum that looks something like this with this big CO2 feature here, and really determine what the major greenhouse gases are in these atmospheres. Okay, so I think for rocky planets, I didn't talk about these first ones, but there's really cool things you can do when you're actually melting or vaporizing the surface of your planet. But for these kind of planets that might have volatiles around them, I think we'll really be able to nail down: do planets orbiting M dwarfs retain their atmospheres? How does volatile deliveries work outside of the solar system? And how do these terrestrial planet atmospheres actually form and evolve over time? So I think that's going to be really exciting. I saw on Twitter last week that I am not the only person really excited about observing exoplanets with James Webb. So on the left here is showing the breakdown of the number of proposals that were for different topics in the HST-Spitzer era, which you can see was 18% exoplanets. And for Webb Cycle 1, this is now expanded to be about 25% exoplanets. So if the time on James Webb is allocated by proposal pressure, I think this bodes really well for us eating some of this. This yellow is extragalactic, so we'll eat some of that time to observe these exoplanets. I will put my concluding thoughts up here that we're transitioning from the HST-Spitzer era, from the first discoveries of exoplanet atmospheres, to really looking at an ensemble of planets with robust detections. With TESS, we're really mapping out our neighborhood. We're finding essentially all of the best targets for future studies of transiting planets. James Webb will allow us to detect atmospheres using high signal to noise spectroscopy and really change the questions we can ask for individual objects. And then I think looking further down the line, we'll get back to this kind of statistical questions for an ensemble of planets with James Webb. So thanks very much, and I will take any questions.
Great, thank you very much, Caroline. That was a very nice talk. And I think these eclipses might even turn out to be more exciting than the eclipse that happened today. So I want to point out that exoplanet category does include disks, though, and planet formation, too.
That's true, yes.
All right, so I see already a couple of people with their hands up. If other people want to raise their hands, I will call on people in the order in which they have raised them. So Alan Voss, go ahead.
Thank you, Caroline. Thank you for a really wonderful talk. It's exciting to see what's going to happen. Do have a question for you. You pointed out that basically the combination of TESS and JW will do a pretty good job on hot super Earths, which is not really quite what we want. Interesting in their own right, but not what we want. People have known for some time that, like papers by Drake Deming and others, saying that, yeah, wow, we're only going to get maybe a half dozen, along with the TRAPPIST planets spectra. Could you just summarize why it is that, I wouldn't say what went wrong, but why is it we can do the hots, but the habitables, just it's the way the molecules that express themselves at those temperatures, or what sort of went wrong?
So why can't we look at habitable planets with James Webb?
The TESS habitable ones. Why? I know it takes an awful lot of JWST observing time just to do the ones like TRAPPIST for like hundreds of hours. So that's a pretty bad penalty there. But just a quick 25 word explanation for a theorist who doesn't know what's going on otherwise.
Yeah, the size of the features scales with the temperature of the planet. So the cooler you are, the smaller the size of the features that you're trying to see is. So that's to first, and it's pretty linear. So that's to first order the hard thing. The other thing is there aren't that many transiting planets in those habitable orbits around the smallest stars. So we have to get lucky, like we got lucky with TRAPPIST, that we have this very small star. So the planet is large relative to the size of the star, and it has planets that actually transit that are in the habitable zone around this nearby small star. So there just aren't that many of those that exist because we're limited to this really small subset of nearby very small stars.
Oh, okay, good. Well, it just gives us all the more motivation to push for LUVOIR and HABEC someday. Thank you.
Yeah, that's right.
Johanna Teskey, you're next.
Nice talk. So I came in a little bit late, so I apologize if you answered this question already, but you were talking about these, trying to match eclipse Spitzer photometry, and how with kind of a very physics and chemistry grounded model, that doesn't work so much, but with a retrieval, like lots of knobs to turn, then you can get a better match. And so I'm wondering, like for that specific case, do you have any like wild ideas about what might need to be added to the grounded model to better make it fit? And then more generally, what do you think is the right balance between the retrievals versus the other method?
Yeah, so I think for this object, I think that it's likely that we're missing some molecule that's in the atmosphere, because for the retrievals to actually fit, you need such a high abundance of CO and CO2 that it's really hard to end up with that. And so I think we're probably missing something that's also absorbing at those wavelengths, and that we are in this regime where there's just not a lot of methane. I've been wondering whether the C to O ratios are actually quite different from what we've been basing it on, which is the sun, and whether planets are just not accreting in something that, within a factor of 2 resembles solar composition as well. Because I think that could change it as well. If you have really carbon rich planets, you end up in this kind of different regime of chemistry. In terms of retrievals versus the kind of self-consistent models, I think you really need both, because we want to take this exquisite James Webb spectra that we're getting and really ask, what is that data letting every knob that we can turn, what is it telling us is actually there? But then, we have that answer that, okay, this is how many parts per million of each of these substances there is. We can't actually connect that to the physics and chemistry unless we have this set of models where we've taken physics and chemistry that we understand and asked, what does that give us in terms of what the abundances of different species and things like that are. And so I think that we'll see a lot of people working together with both sets of modelers to really understand this data.
Can I ask you a follow-up about that, actually, that I was wondering, which is, if you don't know the temperature structure of the planet properly, then the retrievals don't truly give you the parts per million of each molecule, right? So should I trust the C to O ratio that is inferred from a retrieval if it doesn't match what we think is a realistic temperature pressure profile for an atmosphere?
Yeah, it's a good question. So like people in the solar system generally take like a known pressure temperature profile that they have from some other measurement and then just vary the abundances. But we can't do that for exoplanets. We fit it all in one go. And so I think for transmission spectra especially, this can be really challenging to do, because the transmission spectrum doesn't contain that much information about what the temperature structure is. But for thermal emission spectra, it actually does contain a lot of information about the temperature structure of the atmosphere. Like you could see if there was a thermal inversion in your photosphere using the thermal emission spectra. And so I think what we're going to see is that people recognize the value of having both, so that we can take the thermal emission spectra and fit the pressure temperature profile, and then use a transmission spectrum to learn in more detail about the chemistry of the upper atmosphere and put them together.
Thanks. Connell, you were up next.
Yes, I guess I wanted to follow up on that too, because I wonder how unique your solutions are ever going to be, because you have to assume that your atmosphere is highly mixed, it's at equilibrium. If there's no clouds deeper down that are acting as a sink of material. We've already talked about the pressure temperature structure of your atmospheres. How are you ever going to be able to show that you have reached a unique solution? Oh, and of course there's chemistry as well. I mean, and bulk chemistry is going to change.
Yeah, that's a really good question. So, I mean, we know that a lot of these atmospheres are not in, say, chemical equilibrium, right? We can look at the materials that are there and say that these are not in chemical equilibrium. And so to some extent, you're probably not going to end up with a single solution that is the only way to match the spectrum. And, you know, I think about things like these planets are actually not 1D, which is how most of the retrievals have been done. We are not disk resolving them, right? These are 3D objects. We're seeing a sum of all of the parts, cloudy and clearer parts. We're seeing all of that summed together in the spectra that we're seeing. But nonetheless, I think we can, again, look at the ensemble of planets. And, you know, you want to know something like how much material is being sequestered in clouds as they condense in a temperature sequence, right? And then end up below our photosphere and what we're deriving. We can actually measure that because we have a number of planets. We can start to see, okay, the hot ones have this much oxygen, but then as that starts to go into the silicate clouds, we lose, say, 20 to 30% of the oxygen that we started with is now in the silicate cloud. So we should be able to actually map that out by looking at a series of objects instead of just an individual one. But I think we will see exactly what you say. For a single object that we look at, we don't have enough context to tell you exactly what the, say, bulk oxygen and carbon abundances are in that object.
But I guess, don't you need to be able to do single objects if you're going to, for instance, use the metallicity versus temperature scale to say where they formed, if there's been a lot of migration, for instance? So somehow, if you really want to understand planet formation, migration, etc., you need to be able to do it for individual planets, not just ensembles.
Yeah, and I think you end up needing to have a correction, right? Which is done actually in these plots that I showed, where you correct the oxygen abundance for cold objects because you know that some of it has condensed out. So I've been thinking about this for brown dwarfs as well. So the same kind of sequence of cloud condensation happens in brown dwarfs. And if we can map that out in these objects that are the same temperatures as planets, but more massive and much easier to observe, then we can hopefully tie some of that physics in so that we can apply what we think are the right corrections based on the cloud condensation physics when we look at exoplanets themselves.
Thank you. That was very interesting. And I think Faye was next.
Oh, yeah, it's a great talk. And I'm just curious what sulfur as a role in the atmosphere, because most of the talk you're talking about is carbon, hydrogen, oxygen. And my second question is really, what do you have to worry about the atmosphere stratification in order to get some more in-depth overall picture of atmosphere compositions?
Yeah, so to the first question of sulfur, sulfur in gas giant atmospheres is usually really hard to see. That sulfur we think should be mostly in the form of H2S, and it never rises to the occasion where it's always just below the kind of layers that we can actually see because it's not as strong an absorber and not as abundant if it's in something like solar composition. But it will matter for these exovenuses. Those are almost certainly, if we have a CO2 atmosphere like Venus, there's probably going to be volcanic activity on those planets, and it'll outgas probably sulfur dioxide, and that has a strong absorption feature that we think we would probably be able to see. I have an undergrad who's run some simulations of pure CO2 versus a simple model where you take Venus's elemental abundances, and we can definitely see those SO2 features in our simulated spectra. So I think that would be really interesting. Atmospheric stratification is something that we are sensitive to in many of these objects. And so one of the things we probably will see is that when we look at transmission spectra, which probe, because you're looking through a longer path length, it probes higher altitudes. And so what we will likely see is that the chemistry of that might look quite different from when we do look at the same abundances for thermal emission spectra, where we're just looking straight through the kind of hottest part of the planet. And so I think we are likely to see that we say retrieve slightly different abundances, and we can't just add those together like we're looking at exactly the same part of the atmosphere with those.
So I wanted to ask you one question about the silicate clouds, because one thing that I've been working on a lot is the modeling of silicate grains. And so I was wondering what your expectation is for the size, shape, and crystallinity of the silicate clouds. I would assume they're small and crystalline, but.
Yeah, that's a really good question. So in our models, which are really simple models where we're just doing like a mass balance where materials being mixed up and then forming into clouds and then raining back down again, and we balance the masses. In those, we end up with mostly what I would call large grains that are kind of 10 to 100 microns in the optically thick regions of the clouds. And so, but it turns out that those don't actually always match the data that we see. A couple of things in the spectra of, especially for brown dwarfs where we've measured them in better detail, we see that there's evidence for smaller particles in the atmosphere, something like 0.1 to 1 microns, because otherwise you don't get that strong silicate feature. And so I think probably there's a mix of particle sizes from 0.1 up to kind of larger 10 to 100 micron sized particles. People historically had used amorphous properties of what they condense into for their optical constants. But lately we've been thinking that they might actually form into more crystalline kinds of particles, but it's not well studied. But I think it is something that we can test empirically with James Webb, because especially crystalline particles have these nice little crystal features that you can see.
But can you estimate the cooling rates under which those silicate grains form? Because that tells you then whether they should form as crystalline or amorphous.
There's just a lot of uncertainties in the microphysics of how these are actually forming. And so I'm not sure exactly the answer to that as to what the temperature, what the cooling times actually are. But my understanding is that the process by which we would form into a crystal is with some kind of like annealing process where we're taking that particle as it's forming and kind of heating it up as it sinks and then cooling it back down as it rises up in the atmosphere.
Cool, thank you. All right, I don't see any more hands up. So I want to remind the postdocs that there's now an open Q&A and discussion with Caroline that will happen at this same Zoom link. So you are welcome and encouraged, in fact, to stay on after we finish. And otherwise, I just want to thank Caroline again for a really beautiful talk that leaves me very excited about what we may find in the next few years. So thank you.